All right, in this video, we're going to talk about 3.4 Objective 6, where we solve applications involving the product rule and quotient rule. Let's go ahead and look at our first problem here. Let's consider the population function P of t is equal to 100t divided by t plus 2. And we want to find the instantaneous growth rate of the population for t greater than or equal to 0, since time has to be non-negative. So P prime of t is equal to derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. It's going to be 100t plus 200 minus 100t over t plus 2 quantity squared. That's going to be 200 over t plus 2 quantity squared. So this is 200 over, if I expand t plus 2 squared, that's t squared plus 4t plus 4. Here we're looking for. There we go. Now when t equals to 5, that's 200 over 5 plus 2 squared. 200 over 7 squared is 200 over 49. The instantaneous growth rate is greatest at, well, this is a decreasing function here. Let's go ahead and look at it. So 200 divided by x squared plus 4x plus 4. I'm using x's instead of t's there. And I want to, let's see, I think they make me graph this. So 0 to 20. Just go ahead and look at the graph right now. And 0 to I'm pretty sure it's this one. Yes. So see how it's a decreasing function. So it's greatest when t is 0 right here, and it has a value of 50 there. So that's going to be p prime of 0 equals 50. As we go to infinity, the derivative function here goes towards 0. So remember, that's a rate of change. If the rate of change is approaching a slope of 0, the function itself is approaching a constant function, meaning that it has a horizontal asymptote in the graph of some kind, but not necessarily at 0. So the population increases at a nearly constant rate for large values of t. That would be well, we don't know. I know from the graph that it's increasing at a nearly constant rate, but all we know by the limit approaching 0 is that it gets close to a constant value for large values of t. But that is a graph that looks like this. It's increasing quickly, and then it's increasing slower and slower, and it's approaching a constant, like so. So that graph there is the population graph, and then that one there is the rate of change graph. Okay, we've only got one other example here. The magnitude of the electrostatic force between 2-point charges, capital Q and lowercase q, of the same sign is given by the function capital F of x is equal to k, lowercase k times capital Q times lowercase q over x squared, where x is the distance between the two charges, and k is given to us as 9 times 10 to the 9th Newton meter squared per Coulomb squared. To find the instantaneous rate of change, I'm just going to leave k in there and not put the number in for right now. So F of x is k capital Q lowercase q, x to the negative second. All of these are constants. With respect to x right now, x is the only thing that f is a function of. So f prime of x is a negative 2 k capital Q lowercase q x to the negative third, which is negative 2 k capital Q lowercase q over x cubed. And then if we want to make our substitution for k now, this will be negative 18 times 10 to the 9th over, this is q over x cubed, but that's not in correct scientific notation, so I need to move the decimal point back one here and increase the exponent here. So this is negative 1.8 times 10 to the 10th capital Q lowercase q over x cubed, and that is A. They already have the correct units for me there. I don't need to figure out the units. For two identical charges, capital Q and lowercase q of 1 Coulomb, what is the instantaneous change of force at x equals 5/1000ths of a meter? So in other words, you can ignore Q1, capital Q and lowercase q, they're both going to be 1. We want f prime of 0.005 is going to be negative 1.8 times 10 to the 10th over 0.005 to the third, negative 1.8 times 10 to the 10th over 5 times 10 to the negative third to the third. It's negative 1.8 times 10 to the 10th over 125 times 10 to the negative 9th. So this is going to be negative 1.8 divided by 125 is negative 0.0144 times 10 to the 19th. And let's make my calculator give that to me in correct scientific notation. Second EE it's going to be negative 1.44 times 10 to the 17th power. And then let's go ahead and look at the graph here of f prime. So F prime is, let's assume those are ones for right now. So negative 1.8 times 10 to the 10th divided by x to the third, zoom 0. And so we have that f prime of x is negative but approaching 0, so it is, the absolute value is decreasing, yet f prime is actually increasing because it's getting less negative here. So that would be b, the absolute value decreases, and f prime increases as x increases here. So that's it for this video. We'll come back next time and talk about 3.4, Objective 7, where we find higher order derivatives of products and quotients. See you for the next video.